All right, so we are finally at the end of our lesson on binary trees and heaps. This has been a phenomenal journey, a long one. We have covered a huge lot of concepts, starting with a discussion on trees. You know, looking at things like binary trees, complete binary trees, perfect binary trees, learning how to impose these tree structures on lists, and then from there developing heaps, which are basically complete binary trees imposed onto lists. And these have certain properties. For example, in a min heap, all the parent nodes must be less than or equal to all the children nodes. I mean, the values at those nodes must be less than or equal to the values at the children node. We went on to see how heaps help us to solve these priority queue problems in dynamic structures really efficiently. So basically, as we saw, we can create a heap structure in order of n, which is better than sorting, which was at least n log n. Thereafter, as new items come in or existing items leave, we can maintain the heap structure, and this can be accomplished in order of log of n. And this is a very big point. If we had done the sorting method, we spent more effort upfront, we spend more effort in maintaining the sortedness. Heaps do it much more efficiently. So that's exactly what I'm trying to say here, that heaps are an efficient way to solve priority queue problems. Now, before I wrap this up, I just want to go back to two slides which kind of summarize the entire picture really well. First is this slide where we summarize heaps. Like I said, heaps are complete binary trees imposed onto a list of numbers. For a parent node at index I, children are at 2i plus 1, 2i plus 2. For a child node at index I, the parents are at parent is at I minus 1 floor division 2. Remember, every child can have only one parent. Min heap is the one where the value of the parent node is less than or equal to both its children, implies that the root node has the smallest item. Max heap is the one where every parent node, the value of the parent node is greater than or equal to both its children, implies that the root node has the largest item. So this is kind of like a high level summary. Maybe one more point to add, that in Python we have this heap queue module, which makes things much easier to, kind of very efficient, let's say, implementations. The next slide that captures the big picture is this slide. Look, when we looked at the priority queue problem, we had options. We could leave the list unsorted. We could sort the list. We could heapify. Basically, heapify is, yes, effort in the beginning, but lesser than sorting. And thereafter, things become much more streamlined with the heapification. So I think this is really the big picture. Think about it. To me personally, this topic is very interesting. I particularly like the way heaps get disturbed and then they restore themselves back again through percolate up or percolate down. That entire visualization, the entire thought process behind it is, I think, really phenomenal. We are going to learn more about heaps by solving more problems that involve heaps, and you'll see more, that will make it even more clearer. I hope you found this entire journey quite interesting. Do look at our website www.ybyte.in, because as you have realized, we approach programming in a very systematic manner. We enjoy what we are doing, but we are also rigorous about it. Take care and forever enjoy coding. Thank you so much.